Today we begin with a talk by Ramla Abdellatif, who will speak on restriction of p-modular representations of p-adic groups to minimal parabolic subgroups.
Thank you, Luis, for the introduction, and thank you for the invitation to give a talk to this great conference. I guess that as many people here, I wish I was in Valparaiso with all of you, but okay. So as requested by Jessica in her talk, I will share with you my Beamer file on the chat, so that if you want to use it, then you can go. Hope it will be useful. So what I will discuss today is a joint work with Julien Ozeux from Lille University. And the context is something we haven't seen so far, which is p-modular representations of p-adic groups. So in Jessica's talk, we've seen complex representation, we've seen L-modular representation, but with L different from P. And here I will assume P being equal to L. And as you will see, it's quite a mess. So the notations are as follows. P will be any prime integer. So I can take P equals 2 if I want. F will be a non-archimedean local field with finite residue class field of characteristic P. So it's either a finite extension of QP or a Laurent series field over a finite field of characteristic P. And G will be a connected reductive group for now, defined over F. So if you're not familiar with this, as usual, just think about SLN or symplectic group or unitary groups if you like that. And so what we call p-adic group is just the F points of such a group. So here, the point is that it's the same P in p-adic group and in the characteristic of the field of coefficients of the representations we'll be interested in. So just for now, C will be any algebraically closed field of characteristic P. Most of the time, we consider an algebraic closure of the residue field of F, but for most of the thing I will talk, I don't need that assumption. So just for the recall, smooth representations are representations with open stabilizers in the group, in which any vector has open stabilizer in the group. And admissible representations are those that are kind of locally finite dimensional, meaning that if I fix an open compact subgroup of G, then the space of H fixed vectors will be finite dimensional over the base field. And okay, the thing is that most of the time we're interested in admissible smooth representation and in their isomorphism classes. And so to start with, we can just focus on irreducible admissible smooth representation. For instance, because, well, we can dream about having p-modular local Lagrange correspondences. Okay, so we've seen classical local Lagrange correspondence over C, but here we could hope for a p-modular one. And as you will see, it's definitely not a piece of cake. So first thing I want to really stress out is the fact that, well, you definitely cannot expect to have things as in the complex case. So for instance, understanding irreducible representation will not be enough. It's building blocks, but it's not enough to understand that building blocks. So that's basically the second point in these three remarks. If you restrict an irreducible smooth representation to an open compact subgroup, then you won't have something semi-simple. So if you want a counterexample, if you take an irreducible smooth representation of SL2 of QP, like a supersingular one, then you can prove, I mean, that's what we did with Stefano Mora, you can prove that its restriction to SL2ZP is infinite length and its successive extensions of irreducible representation, but it's non-trivial extension, so it's not semi-simple. Another main difference is that this admissibility assumption is really something you have to assume. It's not automatic. Like you have irreducible smooth representation that are not admissible. And so there was one, but at least you can build infinitely many, now you have one, example of irreducible smooth representation of GL2 of a cubic and ramified extension of QP. So it's not something very exotic, which is not admissible. So it has been done by Daniel Lé last year. It's a very short paper and he just built some, okay? So knowing that, you understand that admissibility is like an actual assumption. It's not just coming back. Similarly, assuming that there is or that there is not a central character is really an assumption. It's not automatic in general. And something else for people that are used to complex representation theory is that we don't have any Hall measure here. Okay, we're in characteristic P, so we can't have any Hall measure for p-adic groups. So forget about the harmonical analysis technique. But we have kind of a main result, a key lemma, which is basically an undergrad exercise once you understand what smooth means. It just boils down to the case of P groups, which is the first lemma in Serre's representation of finite group book. So if you take a pro-P group and you take a non-zero, okay, I should say a non-zero smooth representation of this pro-P group, then it has non-zero fixed vector. It's kind of automatic, okay? You always have non-zero fixed vector in non-zero smooth representations of pro-P groups. So that's a lot. In particular, this implies that you can't have irreducible smooth representation of a pro-P group that are not trivial. So if you think about what happens like with depth or that kind of things, you see that you will be stuck very quickly. So you have to think a bit different. But something that I would say doesn't change is that you can always start from the beginning, which is just look at parabolically induced representations, okay? So you take a parabolic subgroup of G, so you fix a Levy decomposition. U here is a unipotent radical, and you take an irreducible admissible smooth representation of this Levy factor. So the parabolically induced representation is defined as follow, like the standard way. There's just no normalization or whatever like that. So it's just functions that are, in some sense, P equivariant with respect to sigma, okay? And the smoothness, if you want this to be a smooth representation, you have some, let's say, uniform locally constant assumption to put on the functions. And what you will call non-supercuspidal representation are irreducible subquotient of such parabolically induced representation for a proper parabolic subgroup, okay? And well, that's quite well understood. So for instance, when G split, then Marie-France-Vignéras in 2008 basically explained how you can have a filtration as P representation of such parabolically induced representation. In the case of rank 1 groups, which will be the one that will be interested in the last part of this talk, I gave like the full description of irreducible subquotient of such representation in my PhD. Okay, a long time ago, but so let's say, okay, non-supercuspidal representation, it's fine, we know where to find them. So now the question, as in the complex case, is are there other such other representations, like supercuspidal ones? So first thing is that it's not obvious a priori that they exist, even if you suspect that they do. And so when F is a finite extension of QP, it's a recent result of Herzig, Koziol, and Vignéras that they always do exist, such supercuspidal representation. So maybe here I should say that, okay, in special case like GL2, SL2, U21, U11, we know beforehand, but because we know how to kind of build such representation, that they do exist, but there was no general result saying that. And so in this paper, they prove that when F is of characteristic 0, you're sure that they do exist. So you're not like suffering painfully for nothing. But the main problem is that we don't have a hand on that. We don't have type theory. We don't have that kind of things. So, well, we're a bit stuck. And here the point is to follow like an idea of Bartel and Livney in the mid-90s, which is, okay, parabolic induction tells you things about non-supercuspidal representation. So when you think about classical type theory, what you see appearing is not parabolic induction, is compact induction. So let's see what we can do with that. And in this setting that I will describe now, what you can do is define what is called supersingular representation. And the upshot is that in the good cases, meaning when you look at admissible representation, being supersingular or being supercuspidal, it's the same. So, so just for this slide, assume that G is GL2, okay, just 2 by 2 matrices, coefficient in, let's say, an extension of QP, but you can take any F as before. So just the usual notation. OF is a ring of integer of F. I fix a uniformizing element pi, and KF will be the residue field. So K, which is the OF point of GL2, is the maximal open compact subgroup of G. So, okay, it's a parabolic subgroup, but here they really use this open compactness properties. And you fix sigma, an irreducible smooth representation of K over C, okay? And you, okay, extend it to a representation of K times the center, which is what I did not by F cross here. The center of G is just diagonal matrices, okay? So it's just F cross, basically. I mean, it's diagonal matrices with the same entries on the diagonal, so it's F cross. So you extend sigma to K times F cross, and you consider the compactly induced representation of sigma from K times F cross. So this is a representation of G, which is quite big in general. And the idea here is to look at the endomorphism of this representation as endomorphism of a G model. And this is what is called spherical Hecke algebra in this context. And one of the main results in two seminal papers of Bartel and Livney in the mid-90s is that actually this big algebra is just a polynomial algebra in one operator, T sigma. And this operator is not very complicated to understand, okay? Basically, if you think of it, okay, there is a way to see this acting on the Bruatis tree of SL2 on which GL2 acts. And on the support of the function, it just takes one vertex and send it on the sum of its neighbor. So it's not something too bad. So if sigma is a trivial representation, that's all you're doing. You take a vertex and you send it on the sum of its neighbor. If sigma is not a trivial representation, okay, you have to be a bit more careful, but that's basically the idea. So it's something very simple. And using this, this operator T sigma, you can build so-called co-kernel representation. So just look at the co-kernel of the endomorphism T sigma minus lambda identity for any lambda scalar. And the point is that when lambda is non-zero, we can describe these co-kernel representations. Actually, they are either parabolically induced representations or extensions of a character by a twist of the Steinberg in one way or the other. So we have non-trivial extension of the character by a twist of the Steinberg, okay? And conversely. And so the point here is, okay, but what happened if lambda equals 0? So if you just look at the co-kernel of the T sigmas, sigma here can vary, okay? It's any irreducible smooth representation of K. And maybe I should say that these representations are not that bad because we have this first lemma that tells you that if you look at a pro-P group acting smoothly on the representation, on the vector space, you have fixed vector. And so here, if you take sigma, an irreducible smooth representation of K, the pro-P radical of K, so for GL2, it's just matrices, the kernel of the reduction mod pi, okay? So this is a pro-P group. So it will act on sigma 2. And the point is that as it's distinguished, it's normal in K, not distinguished, normal in K. Then you can prove that the representation sigma will factor through the quotient of K by its pro-P radical. And it's just a finite group. Here it's just GL2 of KF. So we have like a very nice description of the sigma. It's really nothing mysterious, okay? But what is mysterious is the co-kernel of this T sigma. And the thing is that if pi is admissible, I should have written here this. So if pi is admissible, then saying it's supercuspidal amounts to say that it's a quotient of such a co-kernel, a cohere of T sigma. So you think, oh, cool. If we find out all the quotients, all the irreducible smooth, maybe admissible quotients of this co-kernel, then we're happy. Okay, when F equals QP, Christoph Borel managed to do that, and that gave the first full classification of irreducible smooth representation of a p-adic group in characteristic P, so GL2QP. And this led him to define the first p-modular local Lagrange correspondence in this case. But the point is that if F is not QP, things are a bit more complicated, okay? So, but just here, let's say, now we're happy, we have like tools. We say, okay, we have these co-kernels, so maybe we can try to study them and see what happened. Okay, actually, it's a bit more complicated than that. So if you want to go beyond the GL2 case, first thing we can do is try to mimic what did Bartel and Livne. And this works quite well as long as you look at a group of semi-simple rank 1. I mean, they will act on a tree, and basically you can follow Bartel and Livne process. Okay, there may be some or a lot of extra technicalities at some point, but at least you can do something. So for instance, for SL2F or for unitary groups of signature 2-1 over quadratic extension, but I mean like no assumption on the, of ramification. So I managed to do that in my thesis. So having the same, this very same theorem here, okay. An interesting fact is that a priori, okay, maybe I can say that, a priori, this notion of supersingularity depends on the maximal open compact K that you pick. And the second point here, okay, the equivalence with supercuspidality actually shows you that for admissible representations, at least, this does not depend on the choice of K. And for GL2, you say, wow, up to conjugacy, there's just one such K. But for groups like U2-1, for instance, I mean, even up to conjugacy in GL3 of E, there are several conjugacy classes. So it's really a strong thing to say that it does not depend on the choice of K. And then later, there was Koziol, who did the same thing, but for U11, so quasi-split group now, okay, but in the unramified case. And basically around the same time, there was a big work of Abdellatif and Hertich and Vignéras that managed to define the full setting. So in between, there have been several steps, okay? Maybe I should say that first, there was a work of Florian Hertich for GLN, who give what should be supersingularity for GLN. That was short after generalized by Abe to the split case. And then these 4 people managed to give really general setting for arbitrary connected reductive group of what supersingular representation should be. So it involves, again, the spherical Hecke algebra and some avatar of the Satake morphisms to come back to tori, or maybe should I rather say to minimal parabolic. And the main theorem is that basically, okay, I can rephrase it like that. If you understand supersingular representation of Levy factors, then you understand everything. So it's kind of Bernstein-Zelinsky thing in some sense. If you have an irreducible admissible smooth representation of G, then you can always induce it from a certain parabolic, from a supersingular representation of the Levy factor, tensored by some generalized Steinberg representation, okay? And the triple P sigma Q here is unique. And saying that the representation you start from is supercuspidal, as you assume it's admissible, is the same as saying that P sigma is equal to G, okay? Sounds reasonable, but really it's proven in full generality. So maybe just a few words on the notation and the object appearing here. So there's these Steinberg, generalized Steinberg representations. They really are not a problem because thanks to Tony Lee's work, they are really well understood, okay? So the interesting and mysterious part is this supersingular representation here. So here you start from sigma and P, okay? So I mean, you have P, which is M times U. Sigma will be a supersingular representation of this Levy factor. Then what Abdellatif, Hertich, and Vignéras proved is that you can find a maximal parabolic subgroup of G to which sigma extend. And then the extension is uniquely defined. This is what is called E sigma here. And now you have a triple of parabolic. So you have P and P sigma, and you add a bigger parabolic Q. And this is your triple P sigma Q, okay? So now the question is, what can we say about supersingular representation? Let's just say of groups of small rank, that would already be something. And the answer is not much. So far, there are only 3 groups for whom we have a full classification of irreducible, smooth, and admissible representations. And these groups, so they are GL2QP that I already mentioned before, so due to Borel's work, And that gave the first instance of p-modular local Lagrange correspondence in the beginning of this century. Then in my thesis, I did the SL2QP case, and this gave the first case of p-modular local Lagrange correspondence with actual packets. So here in the GL2 case, I mean, kind of as expected, we had a 1-1, I mean, one representation on the Galois side will correspond to one representation on the automorphic side. In the SL2QP case, you have packets which are generically of size 2. There is one case when it's of size 1. And then later, causal work came up. So U11 of QP squared over QP. And this is the first instance of p-modular local Lagrange correspondence for a quasi-split group. Okay, GL2, SL2 are split, and now we have something quasi-split. And maybe I should say that this work kind of build up on each other. Okay, so my work of SL2 build up on the work of Borel, because something you want naturally is that it's compatible with restriction from GL2 to SL2. So it kind of tells you what you have to do, but now you have to check that it's working, and it's not that easy. And similarly, when you go, how do you go from SL2 to U11? Well, the derived group of U11 is SL2. So again, if you want things to be compatible with restriction, then you know what should the restriction be. And that's how you end up with packets, but that are of a slightly different form than in the SL2 case, because for U11 and like for SL2, you can have characters of the full group, which is not the case for SL2. So you have twists to take into account. And that's all. I mean, so far, there is no other group for which we can say, okay, these are the isomorphism classes of irreducible smooth and reducible representations, even over QP. And something I want to point out here is that all these three groups, they are all of semi-simple rank 1 over F, and they are all quasi-split and then ramified, okay? So, but I mean, for instance, if you take U21, which satisfies the same assumption, then we don't have such a classification, okay? So we have some example of constructions of supersingular representation, but it's kind of not explicit. It's, as I said before, like you take this big co-kernel representation, you relate them to this homology, the homology of the Briatitz tree, and then you show that if you choose well enough your coefficient system, then the H0 will give you a quotient of this co-kernel, so you will have something supersingular. But it doesn't tell you like concretely what is the representation, okay? And it definitely doesn't tell you whether all representations are like that. And the thing is that even for GL2F, when F is not QP, we don't know how to do. So there is a very big work of Borel and Paskunas in which they kind of construct families of supersingular representation. And when F is not QP, they have like far much too many families compared to what we have on the Galois side to expect to find like a natural local Lagrange correspondence between them. Okay. And maybe also what I can say is that even when F is a quadratic extension of QP, it's not easy. I mean, we have a lot of negative results in some sense. So for instance, there is a paper of Benjamin Schran in which he proved that you cannot expect such representation like supersingular one to have finite presentation. So what it says is that basically they will be really ugly, but it doesn't say how ugly they will be in some sense. So let's say that there are a lot of things that must be found here, okay? Okay, and I don't even talk about higher rank because it's even more complicated and even more blurrier. I mean, we don't really see how things go on, even for QP. So let's come back to something more optimistic and say, okay, but what works? And so remember, we started from parabolic induction. So you start from a parabolic subgroup and you build up representation. So one idea that you may have is, okay, maybe we can say something on the structure as a representation of a parabolic subgroup of supersingular representations. Okay, maybe we can like go from G to representation of the parabolic, which means of a levy. So if the levy controls, in a way to explain the structure of the supersingular representation, then maybe we can try to build up stuff. And this is what Paskunas did for GL2 in a 2007 paper, the Compositio paper. So now for just a few minutes, let's come back to the GL2 case, okay? And B here will just be upper triangular matrices. So as I said, the idea is that maybe even if we don't know the representation, we can say something about their restriction, like are they finite length, are they irreducible, can we control the homomorphism when we know what the B homomorphism are, or things like that. And good news is that we can do all of that. So it's this really big and nice result of Paskunas that tells you that if you start from an irreducible smooth representation with a central character of G over an algebraic closure of the residue field of F, then it's at most of length 2, meaning as representation of the Borel subgroup, which means that when I restrict it to B, then I have at most 2 irreducible representations of B that show up in pi. It doesn't say whether it's semi-simple or not, and the thing is that in general, no. In general, it's semi-simple because it's irreducible, but when it's not irreducible, it's not semi-simple, okay? And it's of length 2, if and only if it's a parabolically induced representation. So here, if I should say, maybe I can say this a bit more in detail because it's not, these representations are not very mysterious, okay? I mean, if they are non-supercuspidal, what can happen? Either you have an irreducible parabolically induced representation, and then you're in the case when the restriction to B is of length 2, because you can find the character chi as a quotient, and you prove that the kernel of the projection on chi is an irreducible B representation, okay? Or it's not a parabolically induced representation, but that what can it be? It can be either a character, okay, if you reduce the character to one-dimensional representation to B, it's still one-dimensional, it's still irreducible. Or a Steinberg representation or a twist of the Steinberg representation. And such representation, you can prove that the restriction to B is still irreducible. Okay? Or, so that's the non-supercuspidal case. And now if pi is supercuspidal, then it's supersingular. And basically that's kind of the heart of this first point, is that if pi is supersingular, then its restriction to B is still irreducible, okay? And you don't need to know how pi look like, okay? You can prove that. I will say a word about how we prove that, how he proved that, because the result we have with Ose is that basically we generalize this theorem. And then, so first thing, okay, you know the length as representation of B, and basically you can distinguish a bit between the representation, because if you start from pi, you know that it's irreducible, you know it's infinite dimensional, you know its restriction to B is irreducible. Well, then it's either a twist of the Steinberg or supersingular. And you have other tools at hand to see whether it's a twist of the Steinberg, because it means it would be non-supercuspidal, okay? So it's already something. And the second point tells you that, well, if you want to understand homomorphism between an irreducible pi and any smooth pi, both representation of G, all you have to understand is the homomorphism to their restriction as B representations, which looks more handable in some sense. So this is true if pi is not special series, meaning if pi is not a twist of the Steinberg. When pi is a twist of the Steinberg, then the B homomorphism actually match with the G homomorphism, but starting from a reducible representation, which is the parabolically induced representation from the trivial character. So there is this special case here. But okay, here our goal is, what can you say about supersingular representation? So it's point 1. If pi is supersingular, then the homomorphism between pi and any pi prime are isomorphic to the B homomorphism. So you can just look at the structure as B representation, and I recall you that the first point tells you that P restricted to B is still irreducible here, okay? So again, same question. Can we go beyond the GL2 case, okay? So to see whether we can go beyond the GL2 case, well, you have to understand what is done in the GL2 case. So before I enter into more detail, are there any questions so far? Should I go on?
So far, no questions on the chat.
Okay, otherwise really feel free to interrupt me. So let's try to see what happens. So maybe a first thing I can say, as I said earlier, we are interested in supersingular representations. Here, we really do not need to focus too much on the non-supercuspidal thing because it basically has been done. So for when G is split and you start from a Borel, it's in a Vignéras paper, an early Vignéras paper. And when G is quasi-split of rank 1, it's in my PhD. I mean, the first point is proven for non-supercuspidal representation, and there are partial results about the second point, okay? So now let's see, okay, what are the main tools in Paskunas proof? And basically we have 3 of them. So the first one is this key lemma here, okay, really well-deserved name. So there are a few notation I have to introduce. So here S is just the anti-diagonal matrix 1, 1. So you can think about that as the generating element of the varied group. It's not a surprise. Then you have this T element, the diagonal matrix with first entry, the uniformizing element, and second entry 1, okay? Which is also like, for instance, if you think about Cartan decomposition, it's really playing a crucial role in the structure of G. And then we have this weird operator, not that weird, I will say why afterwards, but weird operator, T, which is basically just looking at the small t, and you multiply it by basically any unipotent matrix coming from the finite field, the residue field. So you have something, okay. And the key lemma says that if you start from a non-zero I1 invariant vector, so what is I1 here? It's the standard Propy-Iwahori subgroup of GL2. So what is it? It's just matrices with integral coefficient, I mean, meaning in OF, okay, whose mod P reduction is upper triangular with diagonal of 1, okay? That's just that. And it's a Propy group. So that's how you know that such a V does exist, okay, because of our first key lemma. There are plenty of key lemmas in this talk. So first thing is that if this operator T sends V to 0, then the image of V under the action of this little s here is in the representation of B generated by V inside of pi, okay? Why is this super interesting? It's because here, as you can see, so first thing, the decomposition of SV does not depend on V in the sense that it's a sum of, let me call that BIs times V, and the BIs are elements of B that do not depend on V, okay? And second thing is that if you think about Brugha decomposition, well, to understand the action of G is understanding the action of B and the action of S. And so what point 1 tells you is that if TV is equal to 0, then the G representation generated by V is the same as the B representation generated by V. So it's really something strong, and it's what will give you this first thing about the control of the full structure by the B structure, okay? But now the thing is that, okay, how do you know whether such a V exists? Like, when do you know whether you can find such a V such that TV equals 0? And the point is that when pi is supersingular, so irreducibility is part of the supersingular definition, but I just write it here for the record. So if pi is supersingular, and if the representation generated by V, but the representation of K, so GL2 of OF, is irreducible as a representation of GL2 of OF, then you can find, so maybe not directly one V, well, maybe you don't directly have TV equals 0, but there is some power of T that will kill V, okay? So, okay, maybe you don't take V, you take T to the n minus 1 V, and you apply 0.1 to it, okay? So these two results together really are the core of the proof behind the Paskunas theorem. And where does this key lemma comes from? Well, this T operator is not showing up from anywhere. So the thing is that it's very close to this T sigma operator I've showed you earlier. You know, this Hecke operator that generates the full Hecke spherical algebra. So the thing is that depending on whether the representation sigma you started from is one-dimensional or not, this T here will either be exactly the T sigma or a shift of T sigma by some scalar. It will be T sigma plus lambda identity. It's not that bad, okay, because lambda is even equal to 1 or -1. So here you really, really use the fact that supersingularity is strongly connected to the vanishing of the action of the operator T, curly T here. Okay, that's really, really important. And the other thing that is really strongly used is the explicit description specific to GL2F, meaning the fact that we have a hand on these co-kernel representations. Okay, if you go in higher rank, there is no such nice co-kernel representation appearing, I mean, not naturally. And being supersingular doesn't tell you that you're quotient of a nice co-kernel representations. So here there is really this specific features of GL2F that comes into the game, together with like really explicit calculation. So if you want to do something else than GL2, well, okay, there is a naive thing. I have tried the naive thing, of course, is you take Paskunas proof and you say, okay, let's see what happened for SL2, for U21, U11. You don't go that far, actually. So for SL2F, I wrote that. For U21 of F, I wrote that, and Peng Xu did it also later, independently, I shouldn't really say. And the thing is that it's not very enlightening. I mean, okay, it's enlightening that you don't want to do that because there are really a lot of extra technicalities that shows up related, for instance, to the fact that you have two conjugacy classes of maximal compact subgroup, or that you have packets. I mean, for instance, you don't have this pi1 for SL2, you must take pi -1 as diagonal element. So it's kind of something which go like 2 steps in the tree instead of 1 step. And so it's kind of leading you to really make a lot of special cases. And you say, okay, I have to do that because technically I can't do otherwise. But well, it doesn't tell you much about the process really, like, okay, like what are the ideas behind? And for instance, it doesn't help understanding why there is this distinction, I mean, on a conceptual way. You understand it technically, because as I said, if you start from an irreducible smooth representation of K sigma, which is, okay, it's always finite dimensional. And if it's a character, then curly T is not T sigma. It's T sigma plus lambda identity. If it's not one dimensional, then curly T is T sigma. And okay, if you try to go for SL2 and U21, you will also have the same assumption, like the same distinction that will appear, but it doesn't tell you why. I mean, it's not very satisfying, okay? And so really the input of our work with Julien is that we give a conceptual interpretations of the calculation and the cases that shows up in Paskunas' work. And it's pretty cool because it gives like some ideas about what you can hope to do in higher rank too, okay? And a consequence of that is that, also our main result is that we can extend Paskunas' result for arbitrary G of F semi-simple rank 1. So in particular, this covers these 2 special cases, but it also gives information on other cases. So I will say a word on that later. So from now on, I will just assume that G is of semi-simple rank 1, okay? Unless otherwise explicitly stated. There's one place when I will not assume that. And so I'm sorry, but I have to introduce a bit more notations. So to help people that are not very familiar with that, I make the parallel with the GL2F case, and also to help you see how it's connecting with Paskunas' work. So you fix a maximal split torus, okay, S. So for instance, in GL2, you just take diagonal matrices. And you denote by Z the centralizer and by N the normalizer of S in G. So for instance, for GL2, what will be N? It will just be the group generated by the torus. And this is matrices anti-diagonal 1, 1 we saw earlier. W will be the Weil group of G. And as I'm in semi-simple rank 1, this will just be S2. So I can pick a generator, an order 2 element. Okay. If you want to look higher rank, you will take a longest longest element in W. Don't know what you will do with that, but you take that. So here W is S, okay, in GL2 case. B will just be a minimal F parabolic subgroup of G, and I assume it has a Levy factor Z. Okay, so I can write B as ZU, where U is the unipotent radical of B. And I can define its opposite Borel with respect to Z, which will have Levy decomposition of the form Z U bar. Okay, U bar being the unipotent radical. So in the GL2 case, B is just upper triangular matrices and B bar just lower triangular matrices. Let me say here that if you assume G to be quasi-split, it really is your life because Z will be a torus here. But we don't need this assumption, okay? A bit more notation. So now we have to define the analog of K and the sigma and whatever. So to do that, you need to fix a special point in the apartment defined by the torus S, the split torus S, in the semi-simple Bratitz building of G. So here, you've seen this Bratitz building in Jessica's talk. It's just a tree, the tree of SL2. The vertices just correspond to homothetic classes of lattices in F squared, in a two-dimensional F vector space. So for instance, just take the trivial lattice, just 2 copies of OF, and you look at its homothetic class. That's a special point in this building. And what will play the role of K, which just be the stabilizer of this special point in G. Okay, G acts on X, and you can look at the element of G that stabilizes X naught. Here it's fixing because it's a vertex, okay? And I don't know what I put an accent, okay, sorry. It's a special parabolic subgroup of G. And this property of being special parabolic and shows you that you can lift W naught. I mean, you can take a representative not only in N, but actually in N intersected by K. So you can reduce it modulo the uniformizing element, and it's really useful in the proof. So here, for instance, K will just be GL2 of OF times the homothetic matrices, because you get homothetic classes, okay? So this is how you see compact group mod center appearing, okay? Here you have to add the center for GL2, for SL2 things are a bit technical, but it's okay. Now we have to replace the pro-p-Iwahori subgroup. So how do you do that? Well, you just come back to the definition of Iwahori subgroups. So you fix an curve in X that contains the special point you fixed, and the point was stabilizer. So really you fixed all the points of the curve, not just the global stabilizer, will be an Iwahori subgroup of G. Okay, let's call it I. I won't use I, but I just say it. And it's why the pro-p radical, this pro-p Iwahori is denoted by I1. It really shows up as the pro-p radical. And as I told you earlier, I1 here will just be matrices in GL2 of OF in the GL2 case that reduced to unipotent upper triangular matrices modulo uniformizing element. And finally, and then I'm done with the notations. Finally, we fix an open compact subgroup, okay, of U intersected with K, so integral points. And we consider the monoid of element that contracts U naught. And surprise, this T element we saw earlier is an element of such a monoid in the GL2 case. So that's wonderful, because you can just take U naught equal to U intersected with K in the GL2 case. In general, okay, you have to pick the simple root, the unique simple root of the root data of GBZ, and look at the co-root, and you evaluate it at the uniformizing element, and this will give you a distinguished Z naught, special thing here, okay? This Z naught will replace T. So this is why in the SL2 case, you see this P minus 1, and in the U21 case, you see P1, P minus 1, that kind of thing, okay. And here are our main results. So we have a candidate for T. You just look at the sum of U Z naught. So Z naught, I just defined it. And now you will just go over all element of U naught mod Z naught, U naught, Z naught inverse. And this makes sense because Z naught contracts U naught, okay? It's really an exercise. I mean, it's just a direct check to see that if you take all this notation we looked at earlier, you have exactly Paskunas operator without assuming anything on sigma. So that's really cool. And the thing is that when you start from a smooth representation of G, then you can make T act on the U naught invariant of pi. okay? So that this does not depend, this thing here does not depend on the choices of the representative in the quotient. So here are the two results. The first thing is, how do you generalize Paskunas key lemma? So that's this key lemma. So if you start from a smooth representation and you take a non-zero, okay, if V is 0, it works too. But the interesting thing is that if you take a non-zero I1 invariant vector, then the action of W naught on this vector is given by upper triangular matrices again. And as in the GL2 case, you can decompose W naught V as a sum of BIs times V, and the BIs do not depend on the choice of V. And that's really crucial in the proofs. And it's really, really nice, actually. And the second thing is that if pi is super singular, then any element of any U naught invariant element, so in particular, any I1 invariant element, is killed by a power of T. So you really have the same lemma as Paskunas, but in this, without all these technical things about you have to distinguish about the dimension or whatsoever. So here I just noted that by definition, supersingular representation here are irreducible, okay? And the main result is that Paskunas theorem holds for arbitrary reductive group of semisimple rank 1. So you know in particular that if you take a supersingular representation of such a group, its restriction to B will stay irreducible, and that the homomorphism as G representation with any smooth representation of G will be isomorphic, will be bijection, to be isomorphic to the B homomorphism. So you just have to understand the B structure. And moreover, we now understand where this like technical assumption come from. So for instance, I told you there is this dimension 1 condition. Actually, it's just a regularity condition. So you understand why it makes things simpler, but actually you don't have to care, okay? So I don't know why I started 56 minutes. So maybe I just want to say a word about the proof really quick, okay? Just before that, so the novelties that this brings, as I said, it covers, not only does it cover all the special cases that has been done so far, but it brings further information, for instance, for non-split groups. So for instance, in Tony Lee's PhD, there was some result about a representation of GL2D with the division algebra, and here we complete some of this result in the non-supersingular and in the supersingular case. And it kind of opened a door for higher rank cases because all the tools that are used in our proofs, they are well defined for higher rank group. But the thing is that it's more complicated than expected. It's an ongoing project. And okay, even for GL3, there are some things. So just so that you know, where does the ID come from and why it's Julien I. So the thing is that if you look at the GL2 paper, Paskunas paper, you see that this T operator, curly T operator, is strongly related to a Hecke action. So you want to see curly T as a spherical Hecke action in some sense, okay? And this is what is related to supersingularity. The formula of curly T, if you know a bit about p-modular satachomorphism, I mentioned earlier, it's really appealing on that direction. You really feel that it should be related. And the idea is to use Emerton's ordinary report functor because these Hecke actions also are involved in the definition of these ordinary reports. And these ordinary reports are related to right cuspidality. But supersingular representation are right cuspidal. And actually, for admissible representation, being supercuspidal and infinite dimensional is the same as being right cuspidal. So it's really strongly connected. So just if you've never seen what is ordinary report, I defined it for you and I explained to you where it's coming from. So that's the only part of the last part of the talk, but I can assume that the rank is arbitrary, okay? So here the references are a paper of Emerton and a paper of Vignéras, okay? And the motivation is as follows. So you know from Frobenius reciprocity that parabolic induction has a left adjoint given by the restriction to the Levy factor, restriction to P, but actually to the Levy factor. And this gives you information on sub-representation of parabolically induced representations. And the question is, well, you want information on quotients too. So can you have a right adjoint? And the answer is, well, if you agree to assume that sigma here must be admissible, which is not a big deal. I mean, in rank 1, basically it's finite dimensional, so it's admissible. If you agree with assuming that sigma is admissible, then you have such a right adjoint. And so Emerton built it assuming that F is characteristic 0, and later Vignéras actually proved that it's working for arbitrary characteristic and even for more general rings that just fit. So here's the formula. So the Hecke action, as you can see, is basically exactly what we did it, okay? The T is the same T as Paskunas, it's Z naught, okay? And, oops, sorry. In the general case, you have to be careful, okay, in the definition of ordinary parts. But direct calculation shows you that when you have a group of semi-simple rank 1, then you can just calculate this. And it's very easy to handle, okay? This X here is just given by the action of Z naught over this, over the U naught invariant. So it's really something very explicit. And in particular, it tells you that, well, the vanishing of odd B, P odd B of pi, is just saying that Z naught acts locally nilpotently on that, which is basically the vanishing condition that appears. Because look, this is our curly T. So the action of Z naught is our curly T. And here you're saying that if odd B pi is 0, then Z naught acts locally nilpotently. So it says that this will be, on each vector, it will, a power of this operator will be 0. So that's exactly what we need. Okay. And the main adjunction formula tells you, so you have to be careful, okay? It tells you that this odd P will be a right adjunct to the parabolic induction from the opposite Borel. But if you look at supercuspidal or supersingular representation, taking Borel of the opposite Borel, I mean, you don't care, okay? So here, the point, as I said, is that now you have that, you know that being supersingular implies that all these ordinary parts will vanish. If you're for a proper parabolic, if you rank 1, that's basically just the minimal parabolic to look at. Okay, and the formula we have tells you that it exactly gives you this vanishing assumption of Paskunas. Okay, so you just have now to play a little bit around with Borel, with Brugha decomposition and Birkhoff decomposition, using some nice induction argument to build sequence of vectors, and you have the proof of our main result. So I'm gonna stop here. Thank you for your attention. And if you have any questions, feel free to ask.
Questions for the speaker?
I have a question. So this sounds like a great result. How much does it help us, on the other hand, to understand how to construct the representation?
Maybe one thing I can say here. So the idea is that you will try to see what was done in the GL2 case to construct supersingular representation. For instance, one thing that may be useful, but I don't know whether it's working, okay? But something that may be useful is the thesis of Emerton-Vignéras. I mean, the thing is that he built some phi gamma models for B, for the Borel. And he managed to build all irreducible representation of the Borel. So in the GL2 case, but his construction maybe carry on in the rank 1 case, at least the quasi-split one, okay? I don't bet, but I think it will work in the rank 1 case. So here you say, okay, if I can like track down which irreducible representation of B come from, I mean, you can track down which irreducible representation of B come from non-supercuspidal representation. So you say, maybe I can try to, okay, kind of take this representation, irreducible representation of B that are not coming from supercuspidal, non-supercuspidal representation, and see how to extend the action of G, whether it's possible or not, and how you can extend the action of G, which means basically just, can you make double U naught act on them? Okay, in the rank 1 case. So that's something you can hope. But basically so far, that's all. I mean, really, okay, having something explicit would be nice, but really here, if we can, I mean, understand well enough supersingular representation, even if we do not build them, so that we see which one will fit in the mod p-Lagrange correspondence, we'd be happy. So.
Thanks.
Very cool.
Great.
Any other questions? If not, let's thank the speaker again.
Thank you.